Okay. Shall I continue, Joy?
Yes, thank you.
Okay, thank you. So, this talk is not about just to give you a complete understanding about causation, uh, but I will try to cover some of the basic idea of causal inference. I hope at some point in your life or in your experience, you have been dealing with the issue of causation, or you have done it. So today I will also share your experience about how you went or how you worked through this basic idea of causal inference. So today I'll give you some brief introduction and give you some motivating example why we need this causal inference framework. And then we also together will define what is a cause, what is causation by definition mean, and also how do we really infer causality from observational data. I hope at some point I am expecting, yeah, you guys are writing your protocol using some of the observational data, and probably you may be interested to do to like look at from causal framework. So that could be an added value. This kind of lecture would be an added value for you for your project development. And also, I will also just briefly walk you through some of the tools that can be used as a causal inference or the methods. Uh, I will discuss about potential outcome. I will discuss about graphical models or the so-called directed acyclic graph. And then next week, we will walk through the structural causal model, and also we'll try to explore some of the methods that can be used to estimate causal effects, like including matching, inverse probability treatment weight, instrumental variable methods, regression discontinuity design, and difference in difference. So before I dive into the idea of causal inference, I want to pause you here and just remember your scientific methods, how we do research. Like within the positivist view of looking at our world, we rely on the basic steps of scientific methods. There are systems or some phenomena that we want to understand. Therefore, we observe and then we pose a question or start hypothesizing the phenomena of interest that we have. And then we do the experiment. And then we analyze our experiment and then we conclude. And our conclusion or our analysis also may, give us another question. And so the spiral of the scientific method continue or goes on. We start from observing, either through hearing, either through our eyes, or from listening expert, or by reading any literatures. And then we continue asking a question. That kind of spiral looping will continue as far as we exist. That is called scientific methods. So imagine our current 21st century world, like the world we are now living in. We dealt with violence, we have recession, we have energy crisis, we have a climate change challenge, we have COVID, we have war, we have poverty. These challenges are really important to be resolved, and let us ask a question about why recession occurred or happened, why we have energy crisis, why the world or the war occurred, or why COVID, why some people remain in poverty, and so on. This kind of question is partly whether we are researcher or uh, uh, whatever. Partly this is part of our nature that we ask a question, why and the cause. When we ask question, our question may be framed into three types. We may ask, sometimes our question may be descriptive, like we are concerned with the process of the process, a condition or organizational relationship, and ask about what is taking place, how the process is taking place. We want to understand maybe stakeholders' view and etc. That is called descriptive. We want to summarize, describe it as it is. But sometimes our question may be a normative question. We want to overall judge the value of the merit or the worth of the change brought about. Like imagine if we intervene some program, we try to compare what is taking place and to what should be. That is evaluative question. Sometimes we may assess activities whether or not the targeted activities are accomplished or not. Sometimes we may also compare whether our interventions are really cost effective or has cost benefit, etc. This kind of question maybe is a normative question. But we have also important question in our mind. Sometimes we may focus on attribution rather than descriptive or predictive, and or sometimes or evaluative or normative question. We may be interested in some of the attribution, like we want to understand about what difference the intervention does really make. That is the most important question sometimes comes to our mind. Whether you are in a public health or in economics or in education or in whatever field, you have some questions. Like a medical expert always ask about the impact of digital mental health on improving child immunization. Because why the question comes, because this digital mental health is becoming ubiquitous, it's becoming everywhere. So it lets you ask question about to what extent this implementation would be effective. Remember when we had a COVID, we were really worried about the extent to which mask can prevent COVID spread. Sometimes, you may wonder about paying the primary health care workers for performance can improve the quality of care. If you are an agriculturalist, maybe you may be really worried about the effect of dam construction on the productivity or malaria distribution or propagation. If you are education expert, you have some causal question, like you want to understand the effect of peer learning on student performance. Like, does class size influence student achievement? And if does, by how much? That kind of question will continue among education experts. If you are a sociologist, you may ask about gun ownership can reduce violence. That is an important question for sociologists. I hope economists also dealt with about social program, like social protection, how social protection could benefit the welfare or could improve welfare. How, for example, access to road, because the policymakers want to have rational allocation of resource. So they may ask, does improving the road could really increase access to labor market or raise household income? If so, by how much? This kind of question is there. We have it always, and we keep continue asking such question. Now, I would expect most of you are more interested in mental health science. So you may be interested to understand what would be the benefit of new drug, maybe introduced in your country. What is the effect of social media on mental health? This is one of the topics that is currently under debate. Does cognitive behavioral therapy improve depression? That is also a question, a causal question. So the goal of any question or any evaluation is to estimate the effect of the intervention. Let's say the intervention is X on the outcome of Y. Let me just give you some story about that we had recently in Kenya. The Kenya government has decided to impose some taxation. There is some financial bill which impose on bread, which used to be tax exempted. Now they want to increase the taxation by 16%. Now that there is some discussion going on in Kenya, if you look at the news in Kenya, there is some uproar, some debate, some concern from the public, etc. The issue, especially the government rationalize why they want to raise the tax is because they want to reduce diabetic and this consequence so-called death. So that kind of question, let us to ask a question like, really, does eating bread kill us? So how do we answer, whether do we know whether really consumption of bread can really cause diabetic or can cause mortality or death? You know, beyond this, the policymakers are really interested about evidence. They want to allocate their resource. They have limited resource. They want to know where they want to be effective. And also for the sake of accountability and also for the sake of credibility, they need some evidence. But some of the policy decision may not be based on evidence. Although we know that the government is implementing so many interventions based on maybe based on intuition, maybe based on some review of the previous study, or based on some normative judgment. But if you look at some of the things that is around us, like for example, if you look at the age restriction for drinking alcohol, it differs from countries to countries. In Kenya, it's about 18 years old, but in Ethiopia, it is 21 years. How did this policymaker come up with this such kind of decision? Should we really have evidence for every action or every program that we have? So the goal of data science is either to describe, as I said, for the question that we have as a descriptive question, we may ask what happened. So who is affected and with who's affected with the condition, etc. Sometimes we may have some question of prediction. What will happen? Who will be affected? We may state like people with X condition are more likely to have Y. This kind of explanation is called prediction. But sometimes we may have causal question or causal statement, like what will happen if, why they were affected. If we change X, how would it change Y is also is a causal question. But if you look at our way of organizing knowledge is either largely depends on association, that we rely on what we are observing or seeing, or we may do some intervention or intervene some of the program or some of the thing that is called intervention, or the hierarchy of like our way of thinking may be counterfactual, like we will try to explore our imagined world or counterfactual world to understand what if I had done this kind of thinking, for example. For example, if you have headache and if the aspirin stopped your headache, you might ask yourself, like, what would have happened if had I not taken that aspirin? Such kind of thinking is called counterfactual thinking. Either we may just simply observe, like someone has taken the aspirin and then the headache resolved, and we may say that, aspirin has an impact on headache, or we may intervene, like give an aspirin to someone who has an headache and see whether the headache will be cured or not. Or we may ask ourselves, like, what would have happened? Like we give the aspirin and the headache resolved. But the question comes here is, what would have happened if this guy or had not taken the drug or had not taken the aspirin? Is called counterfactual thinking. That is very important to organize our way of knowledge of the world, our way of understanding about the relationship between aspirin and headache, for example, if we are really questioning about the effectiveness of aspirin. Imagine you want to evaluate the program, the effect of, for example, cognitive behavioral therapy in improving depression or suicide, etc. So you want to look at, you have, for example, two data points. Before the introduction of the program, you have a treatment group, you have also control group who have similar trend. They follow, for example, if our outcome of interest is depression or suicide, they have similar trend, although the control group are more less likely to develop depression. But the trend groups are similarly, both groups are increasing through time. But when you introduce your intervention, so-called, for example, counseling or CBT, or cognitive behavioral therapy, because of this intervention, those group who receive the intervention might achieve better or might achieve better mental health status as compared to the control group. But had this program was not implemented, the counterfactual or the trend of the mental health status would be the same. This increment is because of the intervention. Therefore, we want to estimate if we are comparing, for example, the difference between mental health status between the control and the treatment, we may end up some bias because our control group might characteristically different from the treatment group, or the treatment group may be self-selected to the program. There's so-called self-selection bias. Or potentially there are some confounders that may like contribute for such bias. Probably those who receive intervention are more likely to be younger age as compared to the control group who are more likely to be older age. So age could be one of the important determinants in mental health. Therefore, it's not because of the intervention, but because of the age. People might get more better health status. Okay. So how do we know? Imagine if we don't have a control group. If we don't have the control group and we have intervened one intervention like CBT for certain group, and after some time we want to measure the outcome of that intervention, and then we want to look at the difference in outcome for the same group with the program, and without the program. The problem here is we can only measure on the same units one status, whether they received the treatment or whether they do not receive the treatment. So we don't know the counterfactual outcome on the same group. The counterfactual outcome is what the outcome would have been for the participant had they not received or participated in that program. Because these groups cannot be observed simultaneously because we cannot exist in two different states. We cannot go back in time, and check whether what would have happened to this group, whether when they receive or when they do not receive the treatment. So what we need is we're trying to look for some characteristics, some control group or comparison groups that have similar characteristics with our intervention. Because we cannot really observe simultaneously two different states. That is called, most of the time, they call it the fundamental causal problem. Because we cannot directly measure the two counterfactual at the same time. If you receive your treatment, when you receive your aspirin, you have already received it. That is the first status. And then we will look at your potential outcome after you receive the treatment. Your headache may go or may not go. And then we cannot see on you that what would have happened had you not received the aspirin. It's difficult unless we have some time machine that we can take you back and see. That is really impossible. Therefore, that means we cannot be on the two states, cannot be both participant and non-participant at the same time. Either you participate or not participate. Either you take the drug or not to take the drug. So that kind of uh, um, challenge give us a difficulty to estimate the individual treatment effect. We cannot really know the individual treatment effect of certain program or drugs. So when do we know, or how do we know that if the program is really impacting the outcome of interest? X is said to be a cause of Y when Y listens to X. As this is a simple explanation or causation. X can be a cause of Y when Y listen X. But how do we know that whether X can cause Y? How do we really, or what kind of methods should we really use? One of the best novel methods called A/B test, or sometimes called a randomized trial. Like in industry, in economics, sometimes they may call it like A/B testing. But it is about randomized controlled trial. One of the best design, or sometimes they call it gold standard, or an ideal weapon for causation is use of randomized controlled trial. Why? Because the design usually randomly assign participant into the treatment and or to control randomly. This random assignment will give us a chance to balance our coverage, it avoids selection bias, and also control temporal relationship. That is one of the main reason why we really like say it's an ideal design to estimate causal effect is use of randomized control trial. It is fairness because we assign randomly our treatment and to our group into treatment and the control group based on random assignment. When it's random or when our assignment is by chance, we assume that the covariates are randomly distributed across population or through both groups. We also avoid selection bias. And also because randomized control trial is moving, like the arrow of time for RCT is moving forward, that's also we can also have a chance to establish causality through temporal relationship. Imagine our goal is you want to understand the impact of or the effect of social media on depression. So RCT is the best design. We select some participant and then split those participants into two groups, to those who we will expose to social media, and then the other as a control. And then we monitor whether the prevalence of the occurrence of depression, and we may conclude that social media has an impact or on depression or not. But imagine, how could we really randomize social media? Look at the practicality, the feasibility, and the ethics of randomization. In terms of time, some of some of the experiment that we want may not be really easy to randomize. For example, if you want to estimate the effect of cigarette smoking on birth weight, how do you randomize? Like, is it ethical to provide some of this cigarette to the pregnant woman and see when they smoke and then see its effect on the birth outcome? That is not ethical. Although most people or scholars really agreed on the standard of randomized control trial, I want to give you some caveats about randomized control. There are also some misconception about using randomized control trial that you have to be careful when you read papers, when you really design RCT, etc. These studies will give you some glimpse, will shed you light about the challenge of a randomized control trial. um, because there are studies who considered as RCT, but they are prone to a lot of bias. But what if we cannot randomize because of finance, because of technical practicality, because of ethics, because the experiment is impossible to set up, because sometimes because it's time taking, some of the outcome may occur after a long period of time. We rely on in that case, we rely on observational or quasi-experimental design. The difference between randomized controlled trial and the quasi-experimental trial is on the power of the control that you have as a researcher. During RCT, you have more power to control who will get the treatment and who will get who will be assigned as a control based on chance, or you assign randomly. The power is on the researcher. But here, in the experimental or quasi-experimental design or in observational studies, we don't have really control over which unit should get the treatment, which unit should not get the treatment. Therefore, there are some people or like authors who really argue that, can we really prove causation from observational data? There are people who really criticize use of observational data as a causal and refer it as a causation. But there are also people who really spending their life to develop a robust method to use this observational data and mimic randomized trials so that we can get the best estimate as unbiased and best estimate as possible. But still, use of observational data is becoming more controversial. Why? Because to infer causality from observational data are more likely to prone to confounders. We said when we use randomized controlled trial or experimental design, we assume that covariates or confounders are randomly distributed across two populations. So the two populations only differ by your treatment or your intervention. Therefore, these confounders will not have an effect on the outcome of interest. That is the assumption that we have in RSATs. But in observational studies, confounders would be the main challenge because we cannot control, have control over these confounders. The other issue is about, observational studies are more likely to be prone to selection bias. Some of the studies may be conducted because people are really voluntarily participating to the program. So we may end up selecting in a selection bias. Like imagine if you want to provide some cash program for certain communities, and if you want to let the community participate by their own decision, probably you are going, since you are going to give money, people may come and join your program as compared to some people may do not. Therefore, if you want to compare the effect of that program on the outcome of interest, maybe those people who are selected to the programs are characteristically different from those who do not, and potentially either underestimate or overestimate your estimation. The other critical thing about challenge about observational studies is about our inability to get the counterfactual ordered. We don't know what would have happened, whether after one group has received, had they not received the treatment, or those group who did not participate, had they participate to the program. So because of this challenge, there are people who really question the validity and the utilities of observational studies. However, thanks for those scientists, yet they start to develop a robust, very interesting methods that we are going to look at. It's like in this session. they developed how to use observational data to mimic randomized control trial. Okay, so we used to hear about this causal inference, causal inference, causal inference. Is it really scientific? Or is it something that's operating in our mind? Like cause is a psychological concept. Are we really fooling ourselves that we understand causation? Do we really understand causation as simple as that? That is a question that we need to ask ourselves again and again. Naturally, as human beings are programmed to ask causal question. I read some interesting book that one of the things that differ us from other animals are because we ask causation, but as other animals don't. But most of the time, despite we claim causality, we may end up uh, some tricky, uh, some tricky conclusion. We learn about cause and effect from the moment we are born. Thinking like how could be different if we do or if we don't do this kind of thinking is part of our daily life. That means naturally, whether we are researchers or not, we are, programmed to ask causal question. But if I ask you, like, if you really check your life, are you really overtuned to draw causal inference from coincidence? Are you like programmed to overestimate or underestimate every incident that you see in your surrounding? For example, why we are tricked, why we are fooled by randomness, because there are two variables that really operate together and that may mislead us. One is a cause of the others. Look at the row, the roster is always growing and the sun will always rise. When the roster crows and the sun rise, these two variables always come together, always daily. First, we hear about the roster crow and then the sunrise. Can we really say that the roster crow is the cause of the sunrise? Or are there any variables between that can cause both the roster to crow and also to the sun to rise? At the same time, there is a study from some ecological studies which shows chocolate consumption is more likely to associated with having Nobel laureate or Nobel Prize. If you look at this kind of graph, or when you read any literature like this paper, you may like mislead like your policymakers or even you yourself as shall I take or should I take chocolate to receive Nobel Prize? And there is also, if you look at sleeping with shoe, and if you sleep with shoe, and if sleeping with shoe is likely um, associated with headache, if you read this kind of paper, and if you look at those paper, they sampled among those people who have already drank alcohol uh, and get up from their sleep. The shoe is not may not be the main cause of the headache, maybe because of the alcohol, may be the main reasons for the headache. Naturally, we are fooled by randomness. Our mental model are usually easy to be fooled by our reality surrounding us. If you look at the first picture, these people might think that they are really, driving, pushing the car, and the car moves. But who knows, we don't know whether they really make it. We don't know how much this cat is really weighing. But if you look at the pictures, the weight of the cat is maybe the cause of the breakage of this roof. Such kind of correlation is always surrounding us. Similarly, if you look at these people, like the number of people who are drawn falling into the pool are more likely correlated with the number of times Nicolas Cage appear on the film. So can we really associate, if you look at this kind of relationship, we may clearly say that, this guy, Nicolas Cage, is the main reason why our people are really falling to the pool. But it's not naturally, it's not true. Why? Look at this. What is the cause of the fire? Usually, sometimes we observe some of the confounder. In this picture, what we observe is the striking the match. Striking the match, we might consider as is a cause of the fire. But if you look at the external knowledge, how the fire can occur, for the fire to occur, we need oxygen. But here we don't observe oxygen. Therefore, when we model any relationship between X and the Y, X is the striking the match, and fire is the outcome of interest. But we should really think about, do we have unmeasured covariates in this knowledge, in this model? Did we really have we really thought about these unmeasured confounders that may be responsible for the cause of the fire? The fire would not have occurred without oxygen. But we did not measure in our data, or we do not have included that variable in our data. But, we may be easily misled as striking the match would be the main reason for the cause of the fire. Here, I want to raise about the issue of unmeasured confounder that you should really take into account when you model. Okay? But comparing academics or researcher and the medias globally, journalists are more bold enough to speak about causation than academics. And, a lot of people are really bold enough to claim causality than academics who do the science of causation. For example, this guy is from Ethiopia. He used to promote about laughter and longevity. He's really bold enough to say that, the more you laugh, the more you live longer. But if you read or try to review some of the studies on this laughter and the longevity, you could not find any RCT or any experimental trial or any evidence that can show laughter could really be associated, can really cause longevity. But because people are tricked, or because sometimes it is really, some of the message are really attractive, people are really getting attracted to this kind of message. If you look at the second picture, is about there is a story about the study from USA, which shows women who eat French diet are more likely to live longer, because in French diet they consume red wine. So when red wine is associated with low fat or less obesity, when media took that evidence to the public, and the public start consuming, for example, in USA, when this publication was released, the sale of the wine increased by 40% within a day, because people want to live longer with less risk of obesity. Similarly, I've raised the issue of Nobel Prize and the chocolate consumption. Like, when you look at more society who consume chocolate, if they more likely to receive a Nobel Prize, it doesn't mean that eating chocolate necessarily letting us or help us to win the prize. So causal inference is the core of the data science, or the core of any science. It's everywhere. It's ubiquitous or omnipresent. It starts from the subject of the causality, start from uh, the creature. When the God, for example, ask, maybe it's one of the main reasons why we were kicked out of this Eden. Uh, God asked, I hope you know this story from the Bible, when the God asked the Adam, have you eaten from the tree which I forbid you? The Adam responded that, the woman who gave me as a companion, uh, gave me and I ate. If you look at the way God asked the question, the response should be, have you eaten? If the question is, have you eaten from the tree which I forbid you? The response should be yes or no. But Adam, without responding directly to the question, he tries to explain the reasons, the cause of why they ate. The girl who the God gave him led him to eat this uh, fruits. And same, when she was asked, she also said, the serpent deceived me so that I ate. This story is just to give you about the moral of the story is just to give you, like, humans are really maybe programmed to explain why. That is a fundamental hallmark of the causation. So always, wherever we do, whatever we do, causality is a very important thing that it plays a role in our life. So to give you some historical account about, the concept of causation, if you remember back in days like 10 or 15 years ago, even now in most scholars, they try to avoid the causal language from the publication or from the writing. The concept has been shrouded in mystery and sometimes considered as a metaphysical or prohibited from its use. Always remember, like 10 or 15 years ago, if you write, this X is strongly associated or causally associated or linked to this Y outcome kind of topics, for sure your advisor or the statistician may really just let you remove such kind of statement or let you to tone it down. But through time, thanks to these scientists, including starting from Aristotle, David Hume, this is Bertrand Russell, and also um, Carl Pearson. Thanks to these science giants, and we are trying to understand causation from it is trying to disentangle from this metaphysical nature to understand our reality. Yeah, there are some scientists who oppose the use because they believe that there is no such cause, there is no such thing, so-called cause or causation. But to date, there are scientists who really keep pushing about the use of causal language as much as possible. We should really aspire causal inference or causal thinking to understand our reality, even to survive. There is a publication you can read about the C word, that is a causal word. Like this guy wrote about scientific euphemisms. Scientific euphemisms is arguing that people are doing causal inference, but they really afraid to claim causality. But there are some scientists who did not really be careful about their analysis, but they are strongly bold enough to claim the causal relationship between the two. So he said this is called scientific euphemisms. Okay, while people use RCT and do very interesting analysis, but they are afraid to use causal language. At the same time, on the other hand, there are people who use, who collect data which is more likely to prone to bias, but they are bold enough to claim causality. and then it is called like euphemisms, like. So try to avoid that kind of thing. If you do aspire causality, just boldly use those methods and write. You are really getting the effect of the program or the effect of that intervention. So this causation historically has the idea of causation is one of the most contentious debates in some of the topics that we had in our history. For example, between 50s and the 60s, about whether cigarette smoking can cause lung cancer, etc. This, if you look at the story behind this is one of the most contentious issues that even today we have, whether cigarette smoking can cause lung cancer or not. Although majority of the evidence tends to believe that cigarette smoking can cause lung cancer, but there are people who still argue about the causal relationship. Even back days in 1950s, this story has broken or divided the family, like the fathers and the child, uh, because of the debate between the two. Same, we have the same story between two, early 70s were by the time we had this estrogen contraceptive discovery. When contraceptive came into this world, women who start to use that contraceptive start to develop this endometrial cancer. And then when they look at and they did the analysis, they found it, estrogen uses are more likely, some of the group from the Yale group, they conclude that estrogen are the main responsible reason for the cause of endometrial cancer. So they really want to just stop that contraceptive use. But there are people who argued from Boston and Harvard group who debate with the Yale group about their analysis, because the sample the Yale group has considered were are more likely to develop cancer because uh, they have some history of cancer, endometrial cancer, and they have also prior other risk of exposure to develop endometrial cancer. So they are arguing that it's not because of estrogen, but it's because of other factors that may be responsible for the cause of endometrial cancer. At the same time, there could be some selection bias between in the first group when they select to estimate the effect of estrogen on endometrial cancer. Similarly, there is a debate about this smoking and the birth weight, the so-called the birth weight paradox. You can read about the birth weight paradox, whether the smoking is really beneficial, among for the birth weight. One of the knowledge that we have is, smoking can cause low birth weight. But there are some studies, really some very nice study who showed uh, women who smoke are more likely to have better birth weight status. So how do we solve such kind of paradox or bias? Is where the applicability or the utility of causal inference or some of the methods that we're going to discuss will help us. And then after 1980s, this is Seaweed Wright, this is Bradford. And then after 98, thanks to these giants, they start to revolutionize. And now, especially very recent years, people are really talking about causal inference and the causation because of the computational power of machine that we have, and also because of the emergence of the artificial intelligence. We are very lucky to live in this era that we start to talk about the causation or causal inference. Let's look at some of the dilemma or paradox that we have in our. For example, if you look at the case fatality rate of COVID, comparing China and Italy, like during the COVID, if you look at the mortality rates or case fatality rate of COVID, the total, look at the total. The more people are dying in Italy than in China when you look at the total. But if you do some subgroup analysis by age, these are more likely common in China than in Italy. So if you are expert on this, epidemiologist, and they give you this graph, how do you interpret? How do you solve? Can we say that Italy has more case fatality rate than China, or China has more case fatality rate than Italy? This is one of the paradox that we are having. Same, you can read about this smoking, current smoking and the COVID. There are people who came out in early 2020, especially around March 2020, who argued about current smoking would prevent COVID infection. And then that kind of publication, even it was published on Nature, and then people start to smoke to avoid that COVID infection. Similarly, if you look at this table, if you want to compare the total deaths rates among people who vaccinated and amongst who do not receive vaccination, if you look at in total, and also if you look at by groups, the death rate between the two groups is completely different. So should we recommend our policymaker to vaccinate or not to vaccinate? When we look at the total, the vaccination, the death rate per 100,000 is less among those who are vaccinated. But if you look at by age group, we may end up with even higher among vaccinated group. But the death rate is very low. Is it because of age or is it because of vaccination? That is a question that we need to answer. So they call it this kind of paradox called Simpson paradox. Similarly, when the outcome of interest would be continuous, like instead of vaccinated or not vaccinated or death rate or not, sometimes if we have some continuous variable, they call it, or Lord's paradox, there is a debate on the effect of diet on weight gain among university students. Okay, so after they start to receive some diets, some people, some men, like boys, are more likely to gain weight than girls. But when these authors invited two statisticians, and the first statistician conclude that there is no evidence of differential effect of the diet on the weight of the student. Because he says use a difference in mean weight gain, neither group gain or lost the weight, thus there is no effect for men and the women of the effect of diet. But the second statistician reported, diet has a larger effect on men. Because he adjusted for the baseline characteristics of the student. So there is a debate on, because of this Lord's paradox, there is a debate on adjusting for baseline characteristics. Is it really important or not? That is a very critical that we need to really answer. So by definition, what we mean when we say causal inference? Causal inference we mean is using observed data to infer causal relationship based on a known or hypothesized mechanism or model. It's about discovering causal structure from the data. That means obviously it's empirically. Causal inference also requires identifying and also estimating counterfactual, which cannot be learned from the data alone. That means we need to really go beyond data to the external body of knowledge about the subject we are interested in, or say call it data generating process. When we want to estimate the effect of, for example, social media use on depression, only looking at the data is not enough. To get the counterfactual world, we need to go beyond the data and structurally understand the relationship between social media and depression from the existing body of knowledge. First, we have to draw the model by itself, then rushing into the data. How? I will let you know later. So, from simple terminology, what is causation, even by definition? When do we say something is a cause? There is some, there's, as the saying goes, there is lucky is the one who has been able to understand the cause of the things. So by definition, causation is a relationship between an event and or the first event and the second event or an effect, known as causality or causation. So causal inference is inferring the effect of any treatment or any policy or intervention on the outcome of interest. So every, by default, every empirical question is a causal. But still, what's a cause? If you look at the Webster Dictionary definition, it says causation, cause is something that brings about result, especially a person or a thing that's agent of bringing something about. Something that brings about a result can be considered as a cause. That is a Webster definition. Husserl also defined as something that make a difference. Can we say if something can make a difference, is it a cause? For example, she argued a variable x is said to be a cause of variable y if y can change in response to change in x is called cause. X can be considered as a cause of y. X is making the difference. But the most important framework of understanding causation is Hume's regularity theory of causation. According to Hume, Hume argued that we may define a cause to be an object followed by another, and where all objects similar to the first are followed by objects similar to the second. That means, on the other hand, it's an idea that an event C causes event E if and only if had C not had occurred, E would not have occurred either. In this definition, there are three important conditions to be considered as a cause. One, when we say an event C causes event E, if and only if had C not had not occurred, E would not have occurred, mean that there is a temporality between the two relationships. The core idea of regularity theories of causation by David Hume is always causes are regularly followed by their effect. That is the hour of time is the cause, is the main first event, and the effect will follow. That is a regular relationship. A cause is a contiguous to its effect. Cause and effect instantiate a regularity. That means always there is a constant conjunction or regularity between the two events. All objects similar to the cause are in A-like is a similar relationship to the object to the effect. There is constant conjunction. That means like whenever you see, most likely, for example, whenever you observe E, you can really say that, C would have already occurred. E would not have occurred had C not occurred. Whenever you observe C, you can more likely say that, E would occur very soon or would occur. That kind of constant conjunction and also temporality is important thing, regularity in Hume's regularity theory of causation. So just based on Hume, Ken Rosman, he's a father of modern epidemiologists. He further, refined causation from the counterfactual thinking, counterfactual reasoning. X is a cause of Y, just in case if X had occurred, Y would have occurred. If X had not occurred, Y would not have occurred. That is a counterfactual definition of causation. That means any event or condition, characteristics that was necessary for the occurrence of the disease at the moment it occurred, given the other conditions are fixed. For example, if you turn on a switch, that is that something that we always do. That's why we say, causal inference is everywhere. Is everywhere where it's in is with us. Like when we switch a light, and if the light doesn't go, what would happen? What was the main reason? If one of the things that we were accustomed to is, when we switch the light on, we always see this light. But someday, at some point t in time, when we switch the light on, we may not see the light. What prevented the light from going on? Between that switch and the bulb, there are a lot of line of explanations that we can give. But we used to have a constant conjecture, constant relationship between switching the line and also having the bulb. Switching and then having the light. But sometimes whether you turn on the switch or not, we may not get the light. But what prevented that light from going on? But sometimes that the previous definition may work for some infectious or some conditions. But there are some phenomena that requires beyond single cause. Like if you think of about non-communicable disease, hypertension, diabetic, or even among infectious disease, that this phenomena may require a multiple of factors. When they come up together, they are responsible to produce or to generate the disease. Like most of the time, we need a component of cause of the model. For example, exposure to someone who has TB does not necessarily result from occurrence of TB. TB always requires a set of factors. Like if someone like sneezes, nearby you, and then you acquire TB, it doesn't mean that you will develop tuberculosis, which is completely different from other infectious diseases. Imagine if this, instead of TB, if we consider like COVID, that's COVID, for example. So in order to have tuberculosis, we need a complete causal mechanism. What are those components of factors that we need that inevitably produce the TB disease? In that case, we need to look at the causation from the sufficient component causal model. We need a set of events without any of which the disease would not have occurred. That is called the whole pie. We need factor A, factor B, factor C, factor D, sometimes unknown factor U. So we need this sufficient cause. This sufficient cause in any offset of this condition, some are necessary within this in these sufficient causes. There are some, each factor are called component cause. For the completion of the sufficient cause, we need this component. Each component should be there to occur to have tuberculosis. But out of this component goes some of the causes are necessary. For example, the poor environmental condition, agent of the tuberculosis, poor living conditions, socioeconomic status, malnutrition, with and including unknown factors would be the main reason for tuberculosis. But out of this, there are some component cause as that is a member of sufficient cause that's necessary and must present in each causal combination of component cause. That's called necessary cause. For example, we may say like the agent of the TB. Okay, you can also check this one. And then 1960s, the Bradford came with the idea to claim causality, we need to really check this criteria. Like even it's difficult, you know, Bradford had not get the chance to look at from counterfactual model, but he put this following 9 criteria just to claim causality. First, the strength of the association between the two exposure and the outcomes should be strong. The consistency of a finding with the previous knowledge should be consistent. Specificity should be there. Temporal relationship, X should precede Y. Those response relationship should be there. That means the more we consume or we have X, the more the Y should occur. That is a dose response relationship. But, you know, sometimes, you know, some of the diseases may require a very little dose. Plausibility. How it's plausible even to justify the relationship between the two variables. Coherence. And should be like confirmed by experiment. And also we need to have some analogy from other disciplines. Like when we explain X cause Y, we should also go to the other field of studies and check whether that analogy exists or not. But now we have another tool to understand causal framework. As an extension of this David Hume's theory of regularity, they developed this idea of potential outcome framework or counterfactual framework. This is one of the tools or the methods that we can use to understand causation or to understand to causal inference. Before I start potential outcome framework as a tool for causal inference, let me stop here. And if you have any like experience or question or suggestion about causal relationship or causation, I would really welcome. Let me give for you to speak about this causal inference. Question?
You can also put your question in the chat, or you can unmute and we can hear from you.
Until we receive question, I may continue the discussion.
Can I ask Joel?
Okay, please.
Yes. Thanks. This is a very nice and clear presentation about all the possible ways to look at causation. So very much appreciated. I want to go back to the sort of last framework of looking at causation. Yes. And I'm interested in the first, strength. Could you give a little bit of detail and maybe even anecdotes or examples on this idea of strength? How strong should the evidence be? I know that, for example, if you have a model that has multiple factors, you could try to find weights or relative weights for each of the factors. And there are sometimes when you decide, okay, this one does not contribute enough, so I am going to take it off.
Okay.
And so I wanted to get your, is there some criteria, or is that sometimes it feels like it's a gut feeling from the statistician to say, okay, this one I can ignore, it doesn't cause so much. But is there some fundamental that you could say? Of course, I understand that sometimes it is because it could have been random, it could have been there by chance, but do we have to find a p-value? What do we base on to say this strength is, strong enough to say it is part of the process?
Yeah. Okay. Thank you. Thank you. Very, very interesting question. Remember your second course about this measure of association. One of the criteria that we can look at strength of the association is using the measure of associations. Jim has discussed with you about this measure of associations called this odd ratio, relative risk, risk difference. And then you can look at the value of that odd ratio or relative risk. And then there are criteria when we should say when we should really look at the odd ratios of that value, and then say, for example, the odd ratio range from, if it is positive, may range from 1 to 3. And the more odd ratio ranges from 1 to the 3, we may say that there is a strong relationship. Like the more odd ratio increase from 1.1 to, for example, to 2.8 to 2.3 or 3, and we may say that is a strong association. Same with relative risk. But these authors have also really gave us some cautious precaution interpreting about this relationship. Because, imagine, we're understanding the nature. But in nature, there is also there is this concept of the strings of the weak ties. I don't know if you've read about the strings of the weak ties. The weak sometimes cause, despite the relationship is weak, sometimes they may cause strong effect. Weak sometimes doesn't mean that they do not survive, but they may cause dangerous, or they may cause a strong effect. But usually we look at those measures of association and define the strengths of the relationship. I don't know if I've answered your question.
Yes, thanks.
Okay, thank you. Any question or experience you have, like from your previous work? Have you considered, like, thought about this causation, causal thinking? Like when you write, do you really worry, like you claim more bold enough about the relation between phenomena of interest that you studied, or do you regret about your previous work? Like, you have done very nice, but you do not really claim as a causality. What is your experience, maybe?
Me, I do this from, I don't know how to call it. This is more like psychology, organizational psychology. And what I was looking at was something called readiness for change, organization readiness for change, all right? And I want to see what contributes to readiness for change. So in this case, you could still say what causes readiness to change. And I had several factors that should be, if they are there, then the organization should be ready to change. In this case, it was change. The change was to implement a digital health intervention, but you can of course apply it to any other thing. So the model should work for any other. And there was some, so I did a structural equation modeling, and I was getting the relative weights of each of these factors, the latent variables. And some of them, of course, had more stronger relationship to the outcome, and others had less. And so my question was, especially because I want to constrain the model, I want to make it smaller or have fewer factors, then I need to say, okay, this one contributes so little, I should take it out. And that's where I'm thinking about, this concept of how strong should the association be for me to say, yes, I keep it or I take it out. I know that when you're trying to do like scale development, you also have to look for how easy is it to use. So you might leave out things and you say, we don't lose a lot of information that way, so we can ignore it. I wanted to see if I can extrapolate from causal inference to think again about how to address this issue. But that is my experience. It's not like, oh, there's a disease A and and cause Y, but it is more like, a state, a psychological state for an organization.
Yeah. Okay. Thank you very much. So here's the thing. I don't know, one of the key message from the previous slide that I want to share the group is about first draw your model before you go to your data. That is one of the message from the previous. Have your own model first and then go to the data. When you go to the data, your data may not be sufficient to explain your model. Where do we get this knowledge of model? Your model would come from review of literature, consulting expertise, from your experience, maybe sometimes your intuition, if your intuition is strong enough. First draw your model and then go to data. And then from the data, you can understand what is missing, what kind of compounders did you measure, what did you miss, what you did not take into account, and what you can consider as unmeasured confounders. Unmeasured because you do not include in your model, or unmeasured because the data was not collected. There are so many things that you can draw your conceptual model before going to the data. And then the data will try to fit your model, if you are lucky enough. Or beyond the data, to have causal inference, I'm saying that you have to go back to the external body of knowledge of the subject or the phenomena of interest to understand causation. Okay, sorry, where is this pointer? Yeah. In order to have a good estimate, we need to have an external body of knowledge or some data generating mechanisms, how the data came into being. And then that gives you either an assumption plus data gives you causal judgment or causal conclusion. Okay. One of the tools that we can use for inferring causation from the two variables is called potential outcome framework. I would repeat this graph. Imagine you have an intervention at some point T baseline, like here. Because of this intervention, let's say the outcome of interest, the outcome of your variable would improve after some time. Had this intervention had not been implemented, what would have happened to this outcome of interest would be your counterfactual world, this broken line. That is an observed phenomena or an observed world, or sometimes they call it the missing data. If you have intervened at certain point time t, and then if for example, the organizational performance increase after some time, had this intervention was not implemented, what would have happened to the organizational performance is a good counterfactual world. So the main purpose of causal inference is about inferring the effectiveness of your performance or the effectiveness of your program or policy. Okay? That you are saying, mathematically, you are saying the program impact is a function of the outcome of organizational performance or disease X or mental health do. That means when I intervene, when I do the intervention, so-called X, or we may write like this, the outcome of interest when I receive the intervention, I receive aspirin, minus when I did not receive aspirin, had I not taken the aspirin. That is my counterfactual world. That is a missing. That is called the program impact. Or sometimes they, especially in economic literature, they may write like this, like the impact of the program would be the outcome of interest Y is a function of like the average effect among those people who receive the intervention. X is equal to 1 means receiving the intervention minus among those who did not receive the intervention. Or if I'm estimating an individual average treatment effect, that means the average treatment effect when I receive aspirin minus what would be my outcome of it, headache, had I not received the intervention, is called the program effect or the drug effect. Okay, diagrammatically. Okay, you have an headache. Let me repeat it. I deliberately repeat some of the example again and again. You want to estimate the effect of aspirin or paracetamol on headache, resolving your headache. You receive or you take your pill and your headache go. Okay? So you may falsely associate, you may say, for definitely you will say, because we are fooled by a relationship between two variables, of course, our headache gone, we may associate like, aspirin works. So we go to our family or to the policymaker, please give aspirin to everyone who has headache. But let's pause and ask ourselves, let's think counterfactually. Had I not received the headache, had I not received the pill, what would have happened to my headache? Could be better or worse? I don't know. This is called the missing world. I don't know. Because I cannot go back in time and check my headache status without taking the pill. The only thing that I have that happened was I have already taken the pill. So I want to estimate the impact of that pill, that is individually, I'm going back in time in machine, the individual treatment effect is this, like the effect after I receive the treatment, the pill, minus the effect without taking the treatment. Or mathematically, or the notation looks like this. We do T means receiving the treatment, and then the outcome, there is observed outcome, and without receiving the treatment, there is an observed outcome. The average between the two would be the individual treatment effect. But there is a fundamental causal problem is I cannot really know or go back in time and see this world. That is called the missing data problem. So that is a mathematical expression. You have every individual, they have a treatment status, they have an outcome status. They fall in either of the states. Either they receive or they do not receive. Imagine if this is random assignment. So this is a missing world. So in order to get that missing world, we need some comparison group, because it's impossible for me to go back in time. So I need to get someone who has some similar characteristics with me, who has headache and did not receive that aspirin. That would be the best comparison for me, so that I can say, the average, rather than estimating the individual level treatment effect, I'll go to the average treatment. Average among those who receive the treatment minus average among those who did not receive treatment would be our estimates. When we assess the effect of any group level intervention or any intervention, our outcome, we are more likely interested in about the difference in mean outcome of the two groups. If assumption we have is if there is no systematic group difference, imagine we are conducting RCT, the average treatment effect is the difference between the two. Very clear. But in observational studies, these two groups may not be systematically similar. That is where we need to be careful when we interpret our finding, when we model, and etc. But imagine this is the RCT world. So we are interested in the average treatment effect of the program or the intervention. So we only just deduce among those who receive the intervention minus among those control. Okay. Let's say the treatment D is a treatment that we are going to take, like some training to improve organizational performance. There are groups who will receive treatment, D treatment, that is training. There are groups who do not receive the treatment or so-called training. So the outcome of interest is the observed outcome for us is, for example, organization performance for each unit. Okay, so we assume that the treatment is, always happening before the outcome of interest. So the potential outcome for the two groups would be the potential outcome for each unit when they receive the treatment, plus or the potential outcome when without the treatment, or when they do not receive the treatment, or why zero is without the treatment. That's for individual I. Okay, let's take a practical example. Imagine we have treated certain groups just without looking into their age. Let's say we treated this group, and we have 8 groups. 4 of them have received the treatment, 4 of them do not. And let's say this program has an effect on survival, like, for example, longevity. And let's say this is a continuous age variable. Like when they receive the treatment, they live up to 8 years old. Imagine if individual, consider this individual go back in time, and if we can see this individual without program, his lifetime or his age would be 60. So we can say that for this individual, the average individual treatment difference or outcome effect is 80 minus 60, this 20. This table shows like it's an imaginary world where we have both potential outcome, when we receive the intervention, when we have also without intervention. This guy, for example, because of the program, he lives longer, and then, okay, without the program, this guy would be 70. That means the average treatment effect of that program would be 5. For this guy, the same, almost 5. Okay, sometimes, doesn't change between the two for some group, for some individuals. Even sometimes they occur negative for others. It happens in our reality. So if you really, without looking at the age, if somebody comes to you, just can you estimate the average treatment effect? For sure, you will add up this. You have already gotten these values, and you will add 20 plus 5 plus 5 plus 10 plus 5 plus 0 plus minus 10 plus 5 divided by 8. You can get the average treatment effect. Imagine if you stopped and thinking, had this program would have some differential effect by age. You should go make some subgroup analysis and look at your data among old age and among young. For sure, just I brought it for as an example, just to let you compute. When you compute the average treatment effect among old age plus average treatment among younger age, you will get more likely older people are more likely to survive because of the program. But when you look at the average treatment effects in total, you may get some, I think, if I remember, it's about 5. Okay, but among all the age group, it would be about 8.75 or something. So this program has more beneficial for older age groups than the younger age group. Similarly, you can also estimate the average treatment effect among the only treated group. Yes, 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 and plus yes. That means you mix the old people and the one young guy, and see the average among the treated. Treat only yes, those who receive the intervention. And then you can also look at the average treatment effect among untreated, among those who do not receive the treatment. No. Just 10 plus 0 plus minus 10 plus 5. That will be quite small. The average treatment effect for both, the average treatment effect would be the proportion of treated among the treated plus the proportion of untreated by among an untreated group would give you the same estimate as this average estimate. That is the formula that I discussed here is also here. This is the average, is the proportion of people who receive the treatment times the average treatment effect among treated minus the average treatment effect among non-treated or untreated without the program. 1 minus D is if they do not receive the intervention. But in reality, we don't have this table, by the way. We have either this one for this guy, or either he participates in the program. We don't know this one. The reality is this one. You go to the data, to the field and collect. Have you received intervention? Yes. No, yes. You will get these values. And you check the outcome of interest. You don't know the other counterfactual world. You cannot get that. And then you may end up rush to conclude that, okay, the outcome, you calculate the outcome, 80 plus 70 plus among those who say yes, minus among those who say no, and you may estimate that the average treatment effect would be some values. And you may say that, the program has an effect. But adjusting for age, without considering, if you estimate without considering the effect of age may have some effect on your treatment status. Age may have also some effect on the outcome of its status. Therefore, you may potentially mislead or underestimate or overestimate the impact of the program. Similarly, you have to also think about the heterogeneous treatment effect. Why? Because our study population are heterogeneous due to some causal mechanisms, or maybe due to some artifacts, like because of bias, selection, misinformation, information, or because of some reasons, our population may be statistically heterogeneous. The treatment might also affect differentially our subject of interest. Naturally, it occurs. Like if you remember the way COVID, the treatment status outcome of COVID management for older people is completely different from the younger. Sometimes the heterogeneity also may arise from the non-randomness, some explainable variable in the direction and the magnitude of treatment for an individual within the population. So in order to handle this heterogeneous treatment effect, you have to really check the real causal mechanism or the cause of that differential heterogeneity. Maybe it's age, maybe it's sex. It's maybe because of some certain groups have differentially unique characteristics. You have to really do subgroup analysis. But that selection of the group should be plausible. We should really, we shouldn't really just divide our sample for the sake of getting p-values or just searching for meaningful interpretation. That subgroup should be based on some causal mechanisms, should have some biological plausible reason why we want to look at differentially, why we want to look at the difference by age, because age would maybe contribute to the treatment and also the outcome of interest. So don't forget the following assumption. The most important element in causal inference is about remembering your assumption. It's not about data. You have to go beyond data and think about these assumptions. Think about your model. One of the assumptions of causal inference is called SUTVA. In whether you conduct RCT or quasi-experimental design, the treatment value, stable treatment value assumption assume that there is no hidden version of treatment. Treatment should be consistent for everyone. Really to estimate or really to disentangle the effect of that intervention, the treatment should be the same, consistent. What does it mean? Remember, if you have already conducted RCTs, example, you have provided some health education for some certain group and control did not receive health education. The way you give health education should be consistently similar for those who receive that intervention. Frequency, dose, language, any vocabulary that used to promote or to educate the people should be consistent. I don't know how much is really practically real, is possible in the real world. But one of the assumptions that we have really to say that it is a cause of the outcome would be is consistency or no hidden version of treatment. The other important point you have to remember is about no interference. The characteristics of those populations who considered as a treated group should not interfere the control group or should not mix with the control group. The treatment status should not influence the control, and the control group should not influence the treatment status or receiving the treatment status. But natural, especially in behavioral or economic or any community-based intervention. Imagine you are performing a very novel interventions in some region, some counties or district. When the control group have heard about that intervention, they may come and receive your intervention without your, although you assign us randomly, like without your approval or without your permission, they may go without even your knowledge, you may go and receive that intervention. There are some non-defiers. If that intervention has such characteristics, you have to really collect that information from your field and make sure that there is no interference. If they have already mixed, if they have already received that intervention, if they do not comply to the status they were assigned, you may end up in bias Therefore, we have to capture those information. The other important assumption that we have is about ignorability assumption. We said RCT is noble or gold standard because confounders are randomly distributed across the groups. We assume that whether it is known or unknown, confounders are randomly distributed. But in observational studies, we cannot really make sure confounders will be the same across population or equally distributed across population. So when we model, when we put our covariate or confounder in our model, we have to make sure that we have really include all confounders. There is no missing confounders. The potential outcome for the group, both groups should for both means for control and intervention should also be independent of the treatment. The other important assumption in causal inference is about unconfoundedness or the conditional exchangeability. You know, this thing, they mix with the ignorability, some of the teams. When we say conditional exchangeability, like the distribution of covariate that we have in a treatment group as compared to the control group should be exchangeable or should be similar, in the other word. Or another word, we are saying that the treatment are randomly assigned. Like if we adjust for age, for example, we are saying that the treatment are randomly or equally distributed across age. That is called unconfoundedness. Monotonicity is about consistency, about we should not really expect defiers. Someone who really decline, like if you assign some group to the intervention, they should not defy. And if you also assign some group as a control, they should not also defy and receive the intervention. But naturally it happens. That's why where we need instrumental variable method or local average treatment effect estimation, we will discuss it next week. Positivity is about having the likelihood or the probability of receiving the intervention should be between 0 and 1. Probability lies between 0 and 1. It's because of some during model specification, sometimes it happens, you may see that the probability is 0 and also a probability of 1. But overall, all units, the assumption of positivity said all values of covariate X present in that population, that means the probability of receiving the treatment is similarly distributed across the population, that means between 0 and 1. That is potential framework, outcome framework. Now, that is potential outcome framework is a way of looking at the data without going to the statistical analysis, without going to the data, like looking at the data by covariates, by potential confounders, and etc. About having a counterfactual thinking before you go to the data, like what would have happened or what is the potential outcome of me had I received the intervention, me had I not received the intervention. Kind of thinking is potential outcome framework. Because I personally cannot go back in time, so I need some group who have similar characteristics to me, so that I can compare myself and see the effect of that pill on my headache, for example. The second important tool to look at that framework, to look at our model. When I say model, what's model? Model is the representation of the reality we are going to explore. As one of my friends said, he's going to explore some intervention on organizational performance. That is the systems he's trying to understand. So he need either counterfactual thinking or tools like DAG or causal diagram. Okay? Why we need that? Just to better understand our knowledge, our world, or our systems we are understanding, we need some diagram, for example. DAG is a visual representation of the assumption we have based on either prior knowledge or understanding that we have. It's a collection of nodes. Nodes, in our case, is a variable, that is X is a node, Z is a node, Y is a node, W is a node, U, a known factor, is also a node. And they are linking with an arrow. The arrow is directing one node to the other node. We are saying, example, X diagrammatically using directed acyclic graph or causal diagram or using a graph. We are looking at our relationship between the variable. Even we are without going to the data, we map this graph. When we look at this graph, for example, we have seen a lot of interesting things. We are arguing X is causing Z, Z is causing Y. That is one of the meanings that we are portraying. Second, X causing W, W causing Z. Therefore, X causes Z through two possible paths. You are arguing when you draw your conceptual diagram or causal diagram or graph. If you draw like this, you are arguing that X is causing Z through two paths. One is through Z, second is through W, and then Z. So if you want to estimate the effect of X on Y, again, you are saying that X is causing Y through Z, X also causing Y through W. First it causes W, then causes Z, then causes Y. Such kind of drawing our causal diagram based on our knowledge about data generating mechanism. Where do we get this graph? I say it's maybe from review of literature, from our understanding experience, maybe by asking review expertise, or maybe if we have a strong intuition, maybe we may use our intuition. So the arrow is about the linking, or the edge is called linking the knots. Why we need? This nowadays, DAG is a very popular approach, increasingly used in the science of epidemiology, genetics, computer, economics, whatever field you have, DAG is everywhere. It's a ubiquitous tool that people are really trying to adopt. Why? It helps us to identify, estimate, by encoding our theory of the data generating mechanism, the whole conceptual framework that help us to analyze the data appropriately to answer causal question. It encodes information about the potential association between variables in the causal network. It is a means of expressing knowledge about the data generating mechanism. It also communicates or summarizes information about the causal structure of the problem, the paradox we have, the bias, the confounding, the selection bias, whatever we have. If we look at diagrammatically, we are more likely to better understand the systems we are investigating. It is qualitative, or non-parametric. You can draw it by reviewing literature. I will show you some steps of drawing causal diagram. It's a key tool to identify the effect of treatment. Like, imagine if you want to estimate the effect of social media among depression. Can we randomize? No, we can't. Practically impossible. How do we manage? So we go to observational data. Look at some people who used social media and some people who do not use social media. Or we may divide Those people who use social media weekly and daily as a treatment, those who use social media rarely as a control, and see its impact on depression. By the time we are seeking this causal effect of social media on depression, maybe age would be the confounding factors that really leads to, old people are really using the social media as compared to young, so age would be confounding. Age would also be one of the important variables that is associated with depression. Most of the depression or the psychiatric problem occur at young age. But these three variables are very simple. Remember the reality we live in. There are a large number of confounding variables are operating in the use of social media, in the use of depression. So it makes our understanding very complex. It's difficult to comprehend even by our imagination. So how do we minimize those confounding variables? How do we put, we may have like a list of variables from 20, 30 variables in our model, but we may end up some in terms of dimension or complexities. So we need to minimize some of the critical confounding variable where application of DAG is as a strong utility. DAG, I said, it's a collection of node and arrow. That's all. Why they say directed? Because it's implied direction. That means I say it's from the theory of David Hume of regularity, if the cause precedes the effect. So it is the term of the arrow is forward. It's so-called directed because of the direction. Why they are cyclic? Because variable cannot cause itself. Either directly or indirectly, they cannot cause itself. But for sure, you have some question in your mind that there is some bidirectional relationship between two variables. Some variables may operate like some cause one, the other cause other kind of bidirectional. If you look at this graph, the whole arrow shows one direction. But naturally, T may also cause CAS. But there is some ways that we can handle in this DAG. But if you do not put any arrow between this variable, you are saying, this is a strong assumption, by the way. You are saying that X does not cause Z. Okay, for example, from this graph, S is not causing X. X cannot or does not cause Z. That is a strong assumption that we have. We have to make sure that we have such kind of strong argument that we do not need an arrow between two variables. So edge is about direction. A cyclic is about because a variable cannot cause itself. So always we need an arrow, but sometimes when you look at a graph like this without any arrow, you are saying that this is undirected graph. So this is not DAG. DAG to be said DAG should be directed graph. Sometimes when we look at the relationship between our variables, remember some of example chronic disease. This X variable occurred during your childhood. By the way, you cannot get diabetic like within a day or within it's not a kind of COVID. Some of the variable, in this graph, there is the issue of temporality, duration, dose, timing. Remember, this is when I put three variables, it doesn't mean that you have to think about in terms of time, in terms of dose, in terms of duration, and then also in terms of the form and the type of X. Does, for example, bread cause diabetic or mortality? So I ate bread. Bread caused something like epithelial damage or some damage in my body, and then it turns to diabetic, like maybe some insulin production affects or cause some atherosclerosis, and then cause diabetic. Okay? But how many loaf of bread did I eat is important here. When did I eat? That's important. Duration and the dose is very critical here. But in terms of time, okay, I ate some of the exposure happened during my childhood, and then they accumulate, and the outcome happened, and the occurrence of this outcome also causes the final outcome, so-called Z. So X and the Y is adjacent, or Y and the Z is called adjacent. They are very close when we say adjacent. They are in terms of time. It's about referring time. But when we look at X and the Z, maybe they are not adjacent. Because they are non-adjacent, because they are too far in terms of time. Some DAGs are incomplete. For example, in the case of randomized controlled trial, it's random assignment is the only reason for receiving the treatment. So we are arguing that there is no relationship between randomness and the treatment, receiving the treatment. So absence of an error is a strong claim. Sometimes you may get some terminologies like X is a parent of Y, Y is a parent of Z, Y is a child of X, and Z is a child of Y. This Y X, so therefore X is an ancestor. Just to improve our understanding, also remember that I have, I don't know, at some point I mentioned one guy called Sewell Wright. He is a geneticist who used this DAG to understand the effect of gene on environment, the effect of environment on our gene. So maybe some of the terminology came because it was usually used from that discipline, okay? So X can be considered as an ancestor of Y and Z, and Y is an ancestor of Z. Or Y is a descendant of X, X. It's obviously true. If you look at, I hope if you are modeling something, you will get this kind of relationship in your graph if you are interested to draw conceptually. Arrow can be bidirectional, but they are not dark. But in order to get the effect of A and Y, remember about temporality and the timing. But it's obviously A can cause Y, Y can also cause A, but in between the two occurrences, there would be some time. Therefore, you can say A1, the first occurrence of A cause Y1, the second Y, and then Y cause A. You can increase, add some arrows as A2, so that you will draw your DAG. If absence of arrow is, I said, there's a strong claim about there is no relationship. This is a direction of relationship. Yeah, you may have also kind of paths. X cause Z through multiple paths. One through M, through Y, through Z. Even X, there are two paths to look at the effect of X on Y, we have two paths. One, X is through M, the other is through Z. When both exposure and the outcome cause another variable, they are called collider. If they collide, or if there is collider in your variable, in your model, they are more likely to be associated. I will show you some of the examples. Similarly, when you draw like this, you are saying B is causing D, B is also causing D indirectly through A. If you look at this graph, you are assuming that B and C are not related. But if the variable of interest, the target estimand you have is to see the effect of B on the C, adjusting for D more likely cause the occurrence of B and C. B can cause C even without drawing an arrow. That's called collider bias. So there are three possible structures that we are fighting in this causal inference approach. One is chain. Always we will look at something occur first, happen, there is some mediator in between, and then the outcome of interest happen. And then this is a fork, so-called, or confounders. When one variable causes both the treatment and the outcome, we call it a fork or it's a confounder. But there are situations where we have collider. When the treatment and then the outcome cause certain condition or certain situations. That's called immorality or collider. Like, two peoples do not have, they may relate because they have adopted a child. You can think in terms of that. This guy and the lady may adopt, but they may not be related. Because of the adoption, we may say that X is related to Y. So in order to avoid our confounding, if we have confounder, we need to really block the path. We need to adjust our condition for confounders. What do we mean by confounders? Is when a variable caused or associated with X or the treatment, when the variable is associated with Y or the outcome, and if there is no effect from the exposure to the outcome through L or through edge, we can consider that variable is confounder. If we want to estimate the effect of A, chronic disease on mortality, this is a front pass. If we do not adjust for age, we may falsely associate the relationship between chronic disease and the mortality. So to get the true effect of chronic disease, effect of mortality, we need to really adjust for age, and then we block the pass. Okay. For the mediator, mediators are the one who is operating in between, like who occur on the second step or second stage. So if we adjust for mediator, when you put in your model, whenever you put in your model, if you adjust for mediator, you may end up in, you may not get the total effect of the treatment or the intervention. So don't adjust for mediator, but adjust for confounder so that you would block the path between the two. But sometimes if you have some common effect of treatment and the outcome, probably you should really, you should not adjust for this. Okay, mediators and colliders are not meant for adjustment. For example, you have seen a lot of people are wearing sunglasses. Now you want to estimate the effect of sun or sunny on hangover. Okay, so if you want to estimate the effect of exposure to sun and on hangover, if you go to those people who have already wearing sunglasses, because during sunny season, people are more likely to wear sunglasses. And when people drink, they're also more likely to wear sunglasses. So if your sample is among these people, you are more likely to end up, exposure to sunny can cause hangover, which is really not the case. Just to avoid that, you should really just do not adjust for colliders. So to help you to understand this, I don't know if I have to stop here and continue next, but I would really prefer you guys to go to this Dagiti. I will put it in a chat box so that you can draw. Yeah, we exercise and close in today's session. Yes, we have a software. We can use, in the next week, I'll show you using R, but today let's start from Dagiti. This is an important tool that you can use for drawing your causal model. Okay. So let me open the arc. Okay. Um, okay. Do you see my screen? Oh, okay, let me put it here. Oh, sorry. Joel, can you confirm it? Okay, do you see my screen on Dagiti?
Yes, now it's on Dagit.
Okay. Now I hope everybody opens his DAG. It's a very simple tool. It's on web. So you go to this launch and you'll get immediately, because this guy has developed and he tried first on this, and then you always see this. But if you want to go to the sorry, I want to remove. Okay. Okay. Now he is saying A is the exposure and the D is the outcome. So you want to model like adjusting for A, or Z, or B is very important. You know, I said if we have so many variables, like let me show some of the examples. I'll respond to some of the questions, Joel. First, let me show. Look at this graph. Have you seen this? I don't know before. You can read this paper. It's about, I think, on gene. You can go to, for example, Paul Zier. Look, the effect of tooth loss or mortality. You know, he wants to estimate this guy. They want to estimate the effect of tooth loss on mortality. They have a lot of confounders and some covariates or risk factors. Okay. So they draw their conceptual causal diagram like this. And then they want to know, you know, because it is infeasible, it is practically not possible to adjust for all of variable, because even it add more complexity. So for which variable should we really adjust to close this path? And then for that, they do it. First, let me show you some of the example. Okay. These people, they want to estimate the effect of warm-up exercise on injury. There is a mediator. Here there is a collider between indices. And then there are confounders. The red path is always a confounder. And then which variables are critical for them to adjust and get the true estimate of the impact of warm-up exercise on injury? That is a question they have. Similarly, you can look at some of these examples. Let me go to the basics of building the new model. Now you have this window. Okay, so when you just simply click, you will get this box, and you can name it like an exposure or whatever exposure you have. Like for you, for example, let's say, let me take this example that I brought. Okay. Let's say our exposure, we want to estimate the effect of vitamins on birth defect. That there is some debates on the effect of having vitamin A would really improve or decrease or increase birth defect. Okay, so vitamin is my exposure status. So I want to look at again, when I click, I will get the birth defect. Okay, I have two variables. Then I have some covariate that I collect, for example, socioeconomic status. Okay, there are some variable I want to adjust, like I collect the prenatal care, whether the woman is exposed to prenatal care, because the knowledge is important. Okay, let me also adjust for maternal genetics. Genetics may be one of the main reasons why people develop birth defect. Maybe the difference in conceiving time, maybe some reason. Or the difference in conceive, let's say. Okay. Now we've collected example, these all variables. Now we want to estimate the effect of the question that we have is the effect of vitamin on birth defect. These are all covariates that we want to put in our model. So to draw this, we just click on those nodes. I said this is nodes. I click the variable on vitamins and the birth defect, and then the arrow comes. Then from my reading, from review, when I review literature, I read that, prenatal care is a cause to receive the vitamin because they are exposed at health clinic, and also not having the care is also main reason for the birth defect. Okay. And then I said genetics is more likely influencing birth defect, but it's less likely, genetics would be the main reason to receive the vitamin or not. I did not get any, I have consulted one expert, read many literature, I didn't get, so I just ignore. Now, I have difference in time of conceiving, that means having pregnancy between the two groups, so I want to check its effect on maybe birth defect. Sorry. So when we get this, you have to click, pause, and remove. Click and remove. The difference in conceiving time is important to predict when to get or when to start prenatal care. Okay, let's say maternal genetics also affect the difference in time, and then socioeconomic status affect prenatal care, prenatal affect birth defect, and let's say socioeconomic status is also a confounder between these two. No, okay, I say this is my conceptual diagram. In order to just nominate which one is exposure, to identify which one is exposure, which one is an outcome, you can click on the nodes, and either you can press E, the letter E, or you can also go to this dialog box and click as an exposure. When I click, it changes to, this, you can look at the legend, it changes to an exposure. Now, my outcome is birth defect. I want to consider as an outcome. Either I click this one, or I can consider or can press O. That's O is an outcome. Because this guy is from medicine or public or epidemiology, so most of the key terminologies that I use are more likely from that. When I say exposure, economists, they may say treatment or intervention. Okay, we talk the same thing, but we may say in a different language. So, when I just draw this, I got very beautiful, but really worrisome pass. The red pass, it says it's a biasing pass. And look at the legend here. You can read. Now, I'm worried. Imagine if I'm modeling this from my mind, like without like looking at conceptually drawing. When I put everything into my model, I may end up, sometimes some bias. But this DAG now is helping me to understand, to get the total effect of vitamin on birth defect. Now is guiding me the minimum sufficient set of covariate I should adjust to estimate vitamin on birth defect is you have to adjust for difference conceiving. To adjust for difference in conceiving, you can also go and click either this box, or you may say this, click and say adjust. When I click, when I adjusted for difference in conceiving, I have already removed some of the bias terms to be there, like the one I wanted. And then it says you also need to adjust for prenatal care. So when I click here and adjust it for it, now all biasing paths will be closed. So I can get, without including socioeconomic status in my model, also without adding, sometimes to be honest, we don't have this genetic from African studies, for example. We don't collect genome data. I mean, rarely we've started, but we have rarely information about genomes, okay, compared to the European. So without including maternal age and the socioeconomic status in my model, by adding only these two variables, I can say, I can estimate the total effect of vitamin on birth defect. That is the beauty of DAG. Okay. So I hope you have managed to use this tool. Any question on this tool, or I may also go to some of the questions on the chat box. Okay. Let's take questions, Joel. Like they can also speak, those who write on this chat box, they can also express their question, explain.
Yes, sure. Okay, Teresa.
I have a question.
Yes.
How do you decide variable is a confounder or a mediator?
Deciding variable, whether based on two. The first is about reading or understanding the data generating mechanism. I said about the body of the knowledge. As a researcher, you are expected to review many literatures, read and understand about the phenomena that you are interested. And then when you read, you will get, date variable, that variables are either is confounder or this is a mediator, or is it the collider? The second one is, okay, you can also go to your data that you collected, but this kind of drawing can be done before collecting even the data. But you can also draw your data and go to the data and check the variable of interest that you may consider as a confounder, or is it as a mediator, or is it as a collider? The variable cause, when we say confounder, if the variable cause is associated both with exposure, also both with the outcome, we can say it's a confounder. Confounding it's a confounding the relationship. Like, imagine, let's say, as I let me take some plain example, simple example. Let's say people swimming. Can swimming is and then this is shark days or days due to shark. People go to swimming and they die. Go to swimming and they die. So okay, you have seen this thing so many times. You may say, you may associate that, swimming is one of the reasons. Swimming pool is one of the main reasons that people are really dying. Also, swimming is one of the reasons people are dying. So you go and sample, and when you see, okay, yeah, the correlation shows like the more people go to swimming, the more likely to die. But naturally, why people go to swimming and when did they go to swimming depends on season. If when you collect that data, if you consider season as a main cause for going to swimming and also attacked by shark, you may say seasons can be as a confounder for both. That is as an example. Same with mediator. All about understanding the nature or phenomena of interest that you have, like, and conceptually draw before you rush, you go to the field. One of the things, we have a challenge in our setup, in Africa setup, is we rush without even understanding the subject and go to the field and collect the data. By the time when you come to the office, we forgot some of the key variables, etc. This is where DAG can help. Okay, any question? Maybe did you get me, or I don't know if I've responded to your question.
Yeah, thank you very much. I think in a more complex system in public health or in other area, variables that are very complicated to assign. You can read as much as you can, but nobody tells you this is a confounder or mediator. So it's a very complicated, in my view, to decide this is a confounder or this is a mediator. It's a very subjective decision, in my view.
Yeah, exactly. The most important step I would take is about starting from prior knowledge. What did the prior evidence say about the variable of the relationship of those variables? And then look at my experience, go to my data, that's my experience, and whether it is consistent with my prior knowledge. And then I can consider. Yeah.
Sorry, I don't want to make it two-way dialogue. When you say prior knowledge, so, there is no, as such, literature telling you this is a confounder or mediator, and there is no literature for everything. And even if there is one literature, it may not be accurate to decide your, your project. So I don't know how much you can trust literature in deciding your project.
Yeah, exactly. When I say prior knowledge and through getting from the literature, for sure they do not really mention that this is a confounder, but sometimes in the methodology they may mention. But what I'm saying is, like, imagine you have some system or body of phenomena of interest you have. For example, the effect of bread on diabetic. So the first question that should come into your mind is, okay, now I want to estimate the effect of bread on cause of diabetic. So how do I expect, what is the mechanism I am expecting bread can cause diabetic? I will go to physiology and read. When I go to the physiology literature, and then I can get some hints about how, when I consume bread, that carbohydrate changed or transformed to certain thing and then cause diabetic. Maybe I can get that information. So I can consider that either as a mediator, or it depends on the reading I have, as a confounder.
Yeah, thank you very much.
Okay, thank you. Okay, there is some concern about that. I will repeat, don't worry. Any question? There is, I've missed. The animal is a woman between giving birth. Patricia, I don't know if she's here. Can she explain the question? I'm not getting. There are many scenarios for one between giving birth period. Patricia, are you there? I'm very happy if you speak to the question, like we want to understand.
Oh, okay. Good afternoon, everyone. Yes, my question is more of I was just trying to understand if because you've given us a scenario, I left the meeting. I didn't have power. So I found it hard to keep on. So I found you explaining or looking at the scenario that you were trying to model. I don't know, using Doug. And there are many scenarios of women between the giving birth period. For example, someone 28 years old, 27 years old, 26, or around 29 that are struggling to give birth or to conceive. Let me see, to conceive. So this has been a concern on my end, and I'm wondering, is it related to what you were doing, or it can be a question on its own? For example, be stated as the cause, wanting to understand the cause of difficulties in conceiving among young women in Uganda. So for me, that is a question. And also in relationship, there is also another question that can come in, that many women, still those that conceive, end up having maybe an operation to help them, give birth. And it was not like that then. So that has also been a concern in my head. So if you can speak to that first question and maybe the second. I don't know if you've gotten it or I confused you.
Yeah, I would say the question, the phenomena of what you have observed about difficulty of giving birth during that specific ages, it is one of the interesting questions by its own. But here, I'm trying to explain, imagine there is a study, studies are really conducted about to estimate the effect of vitamins, whether vitamin, we have immunization program and we supplement vitamin A. We want to know whether that vitamin having that supplementation would really improve birth defect. Because birth defect, spina bifida, these things are very common in African setting exam. So we don't have any evidence about whether vitamin A consumption, can cause birth defect, can improve birth defect, can cause, not cause. So to model that, for example, this paper, they used socioeconomic status, they collected prenatal care, like whether the woman has received this care or not, the timing of conceiving, and also the maternal genetics as one of the coverage when they collect the data. So now if we want to model the effect of vitamin in the birth defect, remember your prior, to appreciate this DAG, you have to remember prior experience. I don't know if you have managed logistic regression or linear regression. Usually we put all variables in our model and rely on model selection. Remember about backward and forward selection of the model. Okay, now we're saying, even without going to the Martian, let's conceptually draw the relationship using DAG. Okay, using DAG, we are giving that vitamin causes birth defect, improve birth defect, and depends on prenatal care. and also depends on time of consumption, and it's also influenced by genetics and socioeconomic status. So when I draw like this and I give to this tool, or when I use R, okay, is it visible, Joe?
Yeah.
Is my screen visible, right?
Yeah.
I'm on Dagity.
Yes, sorry, I was on mute.
Oh, okay, perfect. So when I try to model, rather than putting all these variables, like for example, this is 4, rather than putting 4 of them, let's first conceptually draw our causal diagram. And then this tool guide us which variable is really critical to avoid, to choose variables that we should put in our model, and then we can estimate on the effect of this. The question we have is the effect of vitamin on birth. Why I say this? If you read many papers, people, the original question they have is the effect of vitamin on birth defect. But in their table, they may add this covariate, all covariates. And then their discussion, they start to discuss about the effect of prenatal on birth defect, the effect of differencing on birth defect, and maternal on the birth defect, The first primary question of the researchers were to estimate the effect of vitamin and the birth defect. It's not the primary question is not the effect of prenatal care on birth defect. That's why we may end up, I don't know if you have read, let me share one interesting article about table 2 fallacy. Please read about, like, before coming to a next fallacy, before coming to next session, I really appreciate if you read this concept called table 2 fallacy. We may end up in a false conclusion without, prior understanding the data generating mechanisms, because we may really tend to understand the p-value or tend to read p-values so that we are really like rushed to conclude. So the question that we have, Patricia, is different from the one I'm trying to explain. Okay, for DAG, the question I'm seeing here is about how to add variable. Just simply click, or you can also go to this. Look, there is explanation. When you click this to add a new variable, click tap on the canvas. That means when I click this, okay, I'll say when I click this, I will get some, for example, some variable. I can say Z. So I add variable. So to connect from one node to the other, just simply click the variable and click the second node, and then the arrow comes. That is the way you draw DAG. Okay. Okay, there is a question about, interesting question about causality can be, okay. I saw an article on depression in Sudan using cross-sectional data where they use DAG, but I'm confused because causality is not the same. Yeah, here is what I'm trying to explain. The prior belief that we have about causation is about causality can be inferred only from RCT or longitudinal studies. Now I'm telling you that the world is moving or getting some robust tool, some interesting tool to estimate causality from cross-sectional data, causality from quasi-experimental data, causality from administrative data. So, okay, there's an argument from one of the respondents about he says, hell no, impossible. Still, it is possible. One of the methods that we can use about matching, we will discuss next week, matching using a cross-sectional data. And then we will find some counterfactual group or counterfactual group so that we can estimate the true effect of certain intervention, comparing the prior studies. Maybe, I don't know, if this data is clean, we can also use this John Black's paper and see, yeah, actually they used SCM. Okay, I will show you with the data that I have. I'm preparing, so that's okay. Let's look at and learn how the causal thinking is really adding value to our knowledge. Okay, the material will be shared. It's okay. We'll share with Joel. Joel will communicate to you. And then, I'm not. Okay. So I remain with 2 or 3 slides. Let me finish. And I hope you will exercise DAG before coming next week. Okay. Mm. Oh. Mm. Sorry, I lost my slides. Mm. Okay. Okay. So how do we create the DAG? Okay. The first step in algorithm of DAG is about defining the causal quantity, like stating which one is intervention, which one is control, which one is outcome, and blah, blah. So we have to really understand other causal quantity beyond our phenomena of interest, just to understand the theory behind or the theoretical framework of our model. Either we may put some mediator as an instrumental, or covariate, whatever. We add all quantities to our model. And then we translate. We start writing DAG, drawing, using some of the tools. Yeah, that is the steps. And then check for the assumptions, Make sure that, we have correctly connect those 2 arrows from one variable to another. Make sure that we are really, we deliberately remove some of the arrows. That's also a strong claim. And we need to give some plausible explanation why we connect with the other arrows. It's not about just simply sitting and drawing. It's not about having a picture. It's about understanding the reality, the problem that we are understanding. And then that gives us some confidence, or give us some plausible mechanisms behind those relationships. And if there is some hidden assumptions behind, if there is any source of bias when you link those nodes, that should be really critically thought of and should be captured and start synthesizing your model. That is the at least you can model within 3. You can draw your DAG within 3 or 4 steps. So what is the strength of DAG? People are yet to adopt, especially in African setting. The application of DAG is very limited. So compared to the previous modeling approach, compared to previous statistical inference approach, what is the added value of having DAG in our causal inference approach? It helps us to think clearly and logically about the question that we have, and also to make an explicit assumption about the relationship we are hoping to have. The other limitation of DAG is it's non-parametric, usually made by qualitatively, without any assumption, whether how many variables should be included or not. First you drop all variables, qualitatively based on your reading. But as I showed you earlier, not all variables are really important. We need a minimal, sufficient adjustment to correct to get the total effect of the estimate or effect of the intervention. The other limitation of DAGs are, it shows direction. The arrow it shows line, but doesn't really reflect whether the relationships are negative or positive. It should be upon the researcher's head or mind to think and to state the positivity or negativity of the relationship, negative relationship between the variables. It's just your job to carefully think. Sometimes DAG, we put those model, assume DAG, one of the limitations of DAG is assume linearity. Doesn't tell whether that relation, for example, I put age as a confounder, but age can be nonlinear. That means can follow second order function or quadratic. Sometimes we may put age as a quadratic function. Okay, age squared. But we cannot really just put that age as a linear or as a quadratic function in that model. That is the main limitation that DAG has. So in general, here is the roadmap for you to estimate the causal estimates, causal inference. 1, specify the knowledge about the systems you are understanding. For example, you want to estimate the effect of maternal depression on child development. So you have to really specify the knowledge about what have you really known about the subject between maternal depression and child cognition from the literature, from any experience. What do you already know? What are those assumptions between those relationships to make sense out of your data? Are there any causal quantities or other factors that can be linked to the child's cognition or linked to the maternal depression or can be responsible for the both depression and the cognition as a confounder, or that variables can be considered as mediator, or some variables may be collider. Please, specification of causal model is the primary. We are moving from model to data, the first step. Then go to the data. You go to your data and specify the collected data, whether it fits to the causal model, your causal model. And then what is your causal quantity or parameter you are interested in? Zeta regression estimate, beta estimate? Is it odd ratio? Is it risk reference? You have to clearly specify. Then assess the identifiability, like how much I really take into account confounders, selection bias, information bias, whatever it takes. You have to make sure that whether are you taking the right step to identify the estimate. Then check some statistical estimation problem. What kind of, for example, you assume linear, probably the relationship could be linear, and etc. And then estimate, just do your analysis and start interpreting. That is all what I have for you today. Yeah. If you have any question or suggestion, you are welcome. Joel, it's over to you.
Thank you very much, Dr. Mursu, for a wonderful presentation. Okay, yes, go ahead.
A question is, you have, in terms of mediators, if you have multiple mediators, how many mediators can you handle in analysis? Second question, align with the mediator, they may be correlated to each other. As you said, there may be non-linearity. So is there a way to control the correlation or the correlation among mediators?
like for the first question, I would really say first draw your conceptual diagram, adding all possible multiple mediators you might think of between the two, the exposure and the outcome. And then, and also identify your target causal quantities, I mean, target estimates or parameters. Like, I don't know, let me go back to the Dagiti. Sorry. Let me show you some interesting thing. Here, you know, the main goal of target causal parameters is total effect. We want to estimate the total effect. But in case, if I'm interested on indirect effect of vitamins rather than the total effect, this adjustment may change. You can choose either of these. You know, when you click, when you choose for which variables you should correctly adjust. It gives you some information about for which variables you should correctly adjust. So I'm not sure about how many numbers. I've seen the more we add mediators into the model, especially in the structural equation modeling, maybe add more complexities, have some limited reading, but I'm not sure how many, like to answer like how many mediators can be considered. But I would just generally recommend add more number of variables as much possible as you can. The second question is about checking multicollinearity. I think there is some statistical ways of testing the multicollinearities that you can do. Test of multicollinearity is possible. And then you can remove one if they are highly correlated. You can remove even, that's also important steps in modeling. So you can remove one of the mediators who are really highly correlated as far as they give the same estimates. Variation inflation factor, and there are multiple multicollinearity tests that you can check. But for the first one, I'm not sure. But maybe let me read. There is a book on causal mediation, and I get back to maybe next week. I will start from here.
Thank you very much. It was very good, very clear, educational. Appreciate that. Thank you.
Thank you. Any question? I've seen a lot of discussion is going here. Can we use DAG for association or only for causal effects relationship only? Yeah, you can use for associational relationship, associational, yeah, depends on, like, you know, now we're moving from association to causation. So if we agreed on association, the sum of association estimate has some potential bias. And then DAG is one of the best tools that can help you to take into account those bias. Why you go for association. Yeah. Now we're, you know, just it's about getting the truth. You know, beyond association, when we go to the more causal thinking, we will get the more truth as compared to the previous statistical approach. So yeah, you can use this for drawing. Yeah, drawing your assumption before going to the data it's a good way of practice. But as far as you use DAG, I would really recommend you have to think about the causal link. That is more important for policymakers than estimating association. I'm not discrediting about predictive model, or I'm not discrediting about the value of descriptive analysis. But the causal question, if you have some question about relation between variable, I would really just formulate it as a causal. Exam, if you are moving to refer causality,